Okay, so let's start again this second part of this, where we will continue now with these resonances. And as you can see in these cases that the antennas here are approximately half a wavelength in size. Just give me a second to connect also this one. But it's not really that they are half a wavelength, and there is nothing fundamental in making the antennas half a wavelength long. It's just a convenient way where they approximately work well. So if you think you would like to make an antenna, you can start making it half a wavelength, and then you can cut it to become a little bit shorter, and you can find resonance. And in most cases with antennas, we actually seek resonance. That is what we would like to have. Of course, we will also like then the resistance to be close to 50 ohm. We want both of them to happen. And for a strip dipole, it is slightly below half a wavelength. That's where they sit. We still call them half a wavelength dipole, but they are not really half a wavelength in length, approximately half a wavelength. So if we look at these cases here, we can see that the resonances here are a rule of thumb. So what we are interested in is really this, that the imaginary part of the impedance is 0. So the reactance is 0, which means that in this case, if we will have that, we will have one possibility there, we have one possibility there, and we have one possibility here. Those are the three cases in this graph where the reactance is 0. The one in the middle, you can see up here, it has a radiation resistance that's very high. That is sometimes called an anti-resonance because it comes from the opposite way. It doesn't go from capacitive to inductive, it goes from inductive to capacitive. And for a dipole type antenna, it really means that the current is very low in the feed, which means that in typical cases you cannot use it. But when you come to your patch antenna, it will typically actually sit in this case. It will be similar to that one. So it's not always bad. And then you have the first resonance where you actually would like to be in most cases. And that is the one here that is slightly below. So that's the one there with the pattern that looks like that. The next one here is a typical higher divided current. And if you think what that means for the far field is that it doesn't have a very nice far field. It can be used in some cases. It's not totally useless. But the majority of cases of dipoles is really that you sit here. The sound is not good, or can you not hear me?
I can hear you good.
Oh, that's good. That's good. I got worried there. There was someone who wrote they couldn't hear you. So Khalad, I think then it's something with your system here. Okay, so I continue with these cases. So when we design these antennas, we also would like to have them in some ways as simple as possible and as small as possible. And that means that dipoles, they are really in majority of cases sitting down there. That is what we go for this when we can. So we make them half a wavelength long or approximately half a wavelength long. We have a nice current shape on them, nice radiation properties that we saw last time. So that's where we try to actually do the antennas in some ways. And then it's just slightly off half a wavelength. And that means that we can really see this, that this is some rule of thumbs. And what I mean with the rule of thumbs here is that it's approximately half a wavelength. And the word approximately here is important. So you don't make your antenna half a wavelength because it should be half a wavelength. You make your dipole antenna resonant. You will see this when you do your patch antenna. The first basic design rule we will have for your patch antenna is that you should make it half a wavelength. You will simulate it and see it's not really half a wavelength. And of course, that means you make it what it should be to make it resonant, not to make it half a wavelength. So the same thing in all of these cases. This is what is important. That is a resonance. Sometimes you have to leave it a little bit due to bandwidth and so on. We will come back to that. But resonance is what you would like to be. And you get resonances typically for half a wavelength multiples too. So you get it at 0.5, 1.5, and between them in these dipoles, you get like an anti-resonance. A little bit shifted in these cases. And the motivation for this is that these sinusoidal field distributions, they are somehow solutions to Maxwell's equations. In the patch antenna, we will see this as a cavity solution, which is absolutely correct in those cases. It's an exact solution. They are cavities. In the currents, no, you cannot prove it should be half a wavelength. I know in many cases it's motivated. It almost proved it's half a wavelength, but a simple simulation here says it's not half a wavelength, which means you cannot even try to prove it. You can try to motivate it. You can try to a little bit understand it. But of course, you cannot prove it because it's not correct. But it's a rule of thumb, and it's a very good rule of thumb. So in most cases, it sits slightly below this. You will see it for your patch. You see it here for your dipole. So somewhere around 0.47, yeah, 46 to 48 in some ways. So slightly below, which means that if you would like to make this in practice, is that you do your dipole, you know, let's say you take your dipole antenna here, you try to make it for, say, 1 gigahertz, you have this length, you can measure it, you realize, oh, it's not resonant, it's resonant at the wrong frequency. What do? You take like a pair of scissors, as a traditional antenna design. I will not cut my dipole here. You know, you can start cutting it. It means I can make it shorter. And then I can make it shorter to or until the antenna becomes resonant. So I don't have to really calculate it in those cases. I just make it a little bit shorter. I measure it. No, not correct. A little bit shorter. Not correct. A little bit shorter. Oh, resonant. And I'm happy. So the first start is very good with this half a wavelength. And it gives you the idea where you should be. And then you just make it slightly shorter. And in these cases, it can also be shown that the radius of this is actually having a very small effect on the resonance. There is a tiny effect on it, but it's not a big effect. If you start make it very fat, so you start make it 0.1 L here, it will shift. But if I go in the width that is 0.02, 0.001, now it doesn't change where this resonance is. It will change slightly the bandwidth of this one, and I'll come back to it. So this is a rule of thumb that you should know. Many antennas would like to be half a wavelength. Half a wavelength is a magical number. We will come to array antennas. We have an element separation. Can you guess what it is? Half a wavelength, if we can. If we can afford half a wavelength, we make it half a wavelength. So now we know where we should be. And then, of course, we have to talk about what is the resistance of this. And in the low loss antennas, we call it radiation resistance. So that is only the part that comes from radiation. We assume the losses are low in some ways, and that we can actually compute. So the average power dissipated in antenna is then R here times current squared half. That is the dissipation you get in antenna. And dissipation here, if it's lossy, can be that it's heat and it can be radiation. And if it's low loss, it's only radiation. So then we divide it into these two pieces. So I compute the power here, voltage times current. I put it in and I get the formula I had up here. And that can have an R part and it can have a loss part. So the first part here is then the radiation part that comes from the P rad is R rad. And then I have a loss part, which is this R omega, which is a loss part. So if you think ohmic losses in this case, you can divide it into these two pieces. And if you would like to determine the radiation resistance for a lossless antenna, so let's think they are lossless from the beginning here. What you could compute then is the radiated power that you have here. And then you know that the radiated power is equal to this. And if you know the current in the feed, you can basically divide by the current and multiply by 2. And then you have the radiation resistance, which means that we can use exactly what we learned on the previous lecture because we calculated total radiated power. We knew the current, which means we know the radiation resistance. So that's a good way to find the radiation resistance of these dipole antennas. So let's do that. And what we did in the last lecture is that we calculated the radiated power for a short antenna. So this Hertzian dipole. So let's assume now that this is really short. You can do this for also slightly longer ones, but it gets incredibly difficult. So in this course, we do this because here we gain understanding. If it's longer, we put it into FECO. So this part you should do. I will not remake this now because we did calculate this on the previous lecture. You can see the radiation pattern here coming from this sine square theta, which gives this donut shape. So the max radiation in 90 degrees. That's where you have the maximum radiation. And now we should compute the total radiated power, which means that we should integrate all the radiation intensity over the sphere. So the antenna radiates in all directions around us, and I have to sum up that radiation, which means I have to integrate here over the phi d theta, so the spherical coordinates. I have to weight it with this sine theta, because that was the north pole, which is very small compared to the equator. So that's the weight factor that comes in. And then I sum up all of this, these pieces that I have there. And we did this also last lecture, and the number here is what comes out to these cases. So this is the total radiated power. So now I know the total radiated power from a short antenna, which have a current I0 in the feed, which means I can compute the radiation resistance. So if we do that, I take out my radiation resistance, and that I have here now because the radiation resistance is then connected to the total radiated power, normalize the recurrent squared and times 2. And that was just this formula that we have here. I simplify. And if I plug it in, so I take what I have up here, I have the radiated power, I plug it in there, what I get is these pieces here. So for the very short antenna, you will have a radiation resistance, which is 790 L squared over lambda squared. And now 790 always sounds like a really high number, but this is valid when L is very, very small. So L should be very, very small compared to the wavelengths. So if you look here, you basically can go up to like 0.1. It's a very, very short antenna. And what you can see here, if the radiation resistance comes out, it's a couple of ohms. So when you take your dipole and you push it down much below half a wavelength in length, your radiation resistance really goes down. And that's a very, very common thing, because of course we want to shrink our antennas. We don't want them to be half a wavelength. We want to make them smaller. And a typical thing that you actually get is a radiation resistance which becomes low. And that is of course a huge problem because you cannot match it to 50 ohm. These are not 50 ohm anymore. So that really comes into these cases. Now, if we do it for the half wave dipole, so we assume the current distribution to be this cosine function. It's a very good model. You will see it in the computer lab and so on. It looks like this. It's a fairly good model at least. And then we computed the far field, or we didn't really compute it, but we related to the computation in the appendix that showed that the electric field was like this. Now we can compute the radiation intensity and we can integrate it over the sphere. You can see some details here in Orphanidis of this. We don't do it here. This is very complicated integrals. It doesn't give you any really understanding, but you can do it and it can be computed. And if you do that, you find out that the radiation resistance of this is a little bit more than 70 ohms. So somewhere between 70 and 75 ohms. The calculation here really shows 73 ohms. It can be calculated with many decimals. People have tried to do it, but it's not huge interest to have it more accurate, because as you saw before, your dipole is not even half a wave dipole. It is slightly below. But it has a radiation resistance which is of the order of 70 to 75 ohms. That's where it sits, a little bit above 70 ohms, which is not too far away from 70 ohms. So it will not work terribly with an antenna which is 50 ohm cable. You would need a balloon which also can change these values when they're added. So now we had said that they were lossless. We can determine the radiation resistance. Of course, if we have losses, we have to talk about efficiency of the antenna. So if we now add these pieces of losses, we can see that the low radiation resistance is problematic. One thing is this, that it's far away from 50 ohms, so matching can be harder. It can become a narrow band. We haven't talked about bandwidth yet, but we will talk about it soon. And it increase the losses. And the efficiency now comes that the antenna you have, for example, this dipole antenna, is not made of something that's perfectly conducting. There is a resistivity in this, or conductivity of this. So how well it is to conduct the currents, which means that there are losses there. And the efficiency for an antenna is defined as the radiated power normalized with the total dissipated power. So how much power is radiated compared to what is radiated plus the losses? Which means you can also write this as 1/1 plus the loss divided by the radiation that sits there, which is the same as the radiation loss part divided by the radiation resistance that sits there. And if the radiation resistance is low, as we have here, okay, this might be a larger part of this quotient, which means that the efficiency goes down. So it is a problematic thing, can be a problematic thing to have a low radiation resistance in these cases. And the ohmic losses now come from this finite conductivity of the metals and some typical values here: copper 6 × 10⁷ Siemens per meter in these cases, aluminium a little bit below, steel a little bit below. So it's a very, very high number, but it actually does create these things that you get an efficiency that goes down. And typically then this is also a frequency dependent parameter. And for some antennas, especially millimeter wave antennas, which are popular today, losses can actually be a very, very big problem. And the resistance here depends on the shape of the current. There is something called a skin effect, which means that we have alternating currents, like, you know, they're oscillating very fast. They also push the current to the surface, so they're not uniformly divided over the wire, and that actually increases the losses, so it decreases the efficiency. And then we have the shape along the wire. So Hertzian dipole, we said it was constant. We can have a triangular shape, sinusoidal shape, and so on, and that also affects the losses. And losses typically need to be calculated accurately. We need numerical methods to do it. We can get some ideas of this. And if we look at the dipole efficiency, it depends on many parameters that sits there. We can see when we actually push it up, if we have a good dipole here, we can get a very high efficiency in a copper dipole. But when we start making it shorter, the efficiency will drop. And it depends on what kind of distribution we have over the shape of it. So for example, here, this triangular shape or current constant shape will be slightly higher. But of course, here the scale is very, very short dipoles in some way. So they are far from resonant anyway. But we can get out ideas what efficiency is, and you will calculate it in the computer lab, also efficiencies for this. So the next parameter we have in these cases is the reactance. So the radiation resistance can now be determined from these current distributions. So you could see for the short dipole, we can compute the radiation resistance. We could do it for the half wavelength dipole and so on. The reactance, do you think we can compute that at all? No. We cannot compute the reactance in any reasonable way. It's extremely hard to get out values from the reactance with paper and pen. So again, we will need FEC and software to do it. But of course, as users, we have to understand what it is. So we need to be able to interpret what is this reactance, what is this X that comes out, because it's a very important parameter. And we can determine it from the current distribution in the feed. So we have it from this simple relationship. So the voltage over the current, it has a real part and imaginary part. But we can also think about it as energies, and it gives us some physical picture of actually what is happening with this reactance as we have. We can also use circuit models, and in many cases, small antennas are some resonant circuits. So for example, a small dipole can in many cases be modeled with a circuit which has some kind of capacitance, because it's a capacitive element, the dipole, separation of two metals. We have some radiation from or resistance from the radiation, and then we have some resonance circuit that sits here, which you have some parallel LC circuits. So we can also make circuit models of this. And in many cases, they are, what to say, physically based, but they can also be ad hoc, that you just measure it and you can fit it to some circuit. If you would have a loop antenna, we'll come back to loop antennas next week. There we have more inductive type of antennas because a loop antenna is more magnetic. It's like a current that goes around in a loop. And then you can have a different circuit model. But if we try to make an interpretation of energy of this, we can compute again the complex power. So the voltage times the current complex conjugate, it's the impedance times current squared, and then we can divide it with the resistance and the reactance that sits there. And especially these pieces here of the reactance, that we can show that that's equal to the magnetic energy minus the electric energy. So think again about this, that the reactance X is positive for a coil, J omega L, that's magnetic energy. It's negative for a capacitor, that's electric energy. And the reactance is actually the difference between those. So what that means is that if your antenna has a negative reactance, as the dipole for short lengths, then it's dominated by this electric energy. So a small dipole antenna has a lot of electric energy around it. But then eventually, when you make it longer, it starts dominated with the magnetic energy, and then it starts bouncing back. And at the resonance, there is an equality between those two. So at the resonance frequency, there are equal amounts of electric energy and magnetic energy around you. That is resonance. So as I mentioned there, the reactive power is then proportional just to this difference that sits there. So that is the reactance as we have in antenna, now of course normalized with the current also. And X negative, capacitive, dominated by electric energy. Resonance, the important case, equal amount here of electric and magnetic energy, and inductive, a lot of magnetic energy around your antenna. So at least it can give us some picture of what's happening in these cases. And if we look around a small dipole antenna, then the electric energy is proportional to the electric field. The magnetic energy that we have here is proportional to the magnetic field. And then if you look at the field, as I told you in this course, we will mainly deal with far fields, but here we actually have to look at the near field. And you can see that the electric fields that I have here, so we start with these two, you can see they have components here, 1 over r and 1 over r2 there. So this goes as 1 over r squared. The same with this one and this one. If I look at the magnetic energy here, you can see it goes as 1 over r2. And then we have the dominant part, which is the far field, which is what we've really been looking in this course. Here we have this one, and we have this one. This is the far field terms. The other ones are the near field terms. And now if r is small, then of course the electric field is dominating because you divide by a very small number. And that means you have this electric field that really dominates the cases when kr here is very small. So k was the wave number, r the radius. And if you make the antenna very, very small, it's basically only electric field that's pumping there. And that means also the antenna is capacitive. It's electric energy around it that sits around the antenna. So that is some interpretations of these antennas. So in some ways, it's hard to get reactance, but you need to know it because you have the resonance frequency you need to determine for antennas, one of the most important parameters. And you need to, in some way, search that one when you design your antenna. Like your patch antenna, you should try to make it resonance at the Bluetooth frequency. That means you have to have the right length of it. And then how do we do this when we cannot really do it by paper and pen? And that is that we don't actually know what the current is on the antenna. And this is a case where we need to let the computer instead tell us what it is. So I will show you this, and then we will come in a little bit to bandwidth, which we can get out when we actually have determined the currents from a computer, and that can simulate it for us. So in some ways, what we have done so far in the course is that we determine the radiated field and current density on the antenna. So the radiated field from a given current density. we have analytic expression for Hertzian dipoles. So these antennas, which are really, really tiny compared to wavelengths. We assumed a current distribution here on the dipole. It's very good assumptions. And for example, for the half wave dipole, it works really well. Of course, it's not exact, but it works within a few percent in some ways. But what do we do when we do not have these good assumptions? So if you have another type of antenna, how do you do? How do you determine the current of your antenna? Because we need it, as you see now. I mean, the reactance is very important. We need to get it out. And what that means is that we need methods to compute it, but it's not methods that we can do by paper and pen. We have to let the computer do it for us. So what we in some ways do in the simplest view of it, and that's actually what you will use in the simulations when you simulate it in FECO, is that you divide here the current density into very small elements. So very, very tiny pieces. And every little tiny piece you can think about the Hertzian dipole. That's approximately what's happening. And then you can determine the radiated field from all of those small elements. We know what it is, that we can easily compute. We have actually done it in these cases. And then we add Maxwell's equations. And Maxwell's equations adds what's called boundary conditions. So they put constraints on these currents. And for example, for a good conductor, that is PEC, perfectly electric conductor, it says that the electric field has to vanish on top of it. And this gives us a matrix equation, a linear system that we can solve. And we solve that numerically. And that is, for example, what's done in FECO. Of course, we could do this by paper and pen too. So why don't you think we do it here? I mean, we do calculate quite a lot in this course. I hope probably enough for you. But why don't we do this by paper and pen? If you start thinking here, I start saying here that we have to divide it into many small parts. Basically, each of these small parts has one Hertzian dipole, which means it is one unknown in my matrix equation. And if you think that when you have solved matrix equations, you know, two unknowns, it's quite fun to solve a matrix equation with two unknowns. Three of them start to get a bit hard. And I think you never made more than three in any of the linear algebra courses you have solved. And if you think about an antenna, you divide the current into three pieces, it's nothing. We typically need 100, maybe 1,000 of this, which means our matrix has a dimension of, say, 1,000. You cannot do that by paper. So we really need a computer to do this for us. They need to solve this for us. So what it means is that I take my antenna and I say it's short dipoles everywhere. I do really simplify description of this. So I can draw this that the current here is very short here. You can see it has a direction. The length of the arrows is proportional to the magnitude. So it's maximum value here, and then it's shorter here again. Another way of drawing the same is that I draw the amplitude here as the height that comes up above it. And then I can actually determine the electric field that comes out of these ones. So that I can do. Now I assumed it was in the Z direction. That looks like this. And of course, in a computer, you can do it from other directions. I can just not write it up here by paper and pen in a simple way. So I can compute what the electric field is in these cases. And it's proportional in these cases to what I have for amplitudes of this one, for example, the currents. And then I take the sum of this, and on every metal, I say it has to be equal to 0. And that will give me a linear equation that I can solve. It's called an integral equation you write up for this. We will look a little bit on that later in the course. So by then synthesizing the total current that you have on your dipole, it's then the sum over these small Hertzian dipoles. Because this one, I can say is instead this one plus this one plus this one plus this one. That gives you this nice cosine type shape. But now I would have one unknown there, one there, one there, one there, and so on. And this is what you solve in the computer. They determine the amplitudes on these ones, both amplitude and phase. So if you look at on a typical case, you will get out. So if we take a dipole antenna, here you can see a dipole antenna. And now you can see here that I have some numerical mesh because you can see some triangles there. So imagine one dipole on every of these edges of this triangle, basically. That is what's happening there. And then you say those are unknown. You say you can solve the equations for these ones. And you do that by expanding this in basis functions, which are these dipoles. You have your coefficients you would like to know, so you determine this one. That is what FECO computes to you. Then you know your current density. And as soon as you know your current density, you can compute your far field and you can compute your input impedance, so you get your reactance. That is what the computer gives you. And the far field is computed exactly as you have done in the course. So we just take the radiation intensity, we integrate with respect to this phase factor that sits there, and now this only lives on the surface, so I only integrate this over the surface. We typically had it in integration over a volume. And that will give you the far field. So from that you can get this pattern that you get here, and you will have it in your computer lab, where you can see this radiation pattern. So how is the radiation distributed over space? And you also got out this current. So in this case here, we can see a plot over the current. You can see here, this is some amperes per meter in some dimensions. The highest current in here and lower out here, basically zero on the edges. So if you plot the amplitude on this, you will have this type of cosine shape. Higher amplitude in the center, lower on the edges. So that we can now get from this solver. And then, of course, if you have done that, you can take the quotient between that current and voltage. That's the input impedance. And then you can compute the reflection coefficient. So exactly the parameters we would have out. But we have to let the computer determine the current. The current we cannot do by paper and pen for these cases when we want more advanced things in some cases. So this is what you will get out in typical cases here. So this is the input impedance of a dipole. And in this case, we should see if we know the length of it. I should have written it up. Yeah, okay, at least we can see here the resonance frequency. Then you go in and see where the imaginary part here, the reactance is 0. You can go down here and you can see it's around 2.8 gigahertz. And if you would like here, you can compute the resonance wavelength then, and you can compare it with the length, which is in that case for 0.47 lambda 0. So similar to half a wavelength as we had before, but not exact. And then you can look at the reflection coefficient. And now if you match it to 50 ohm, yeah, you can see here that totally mismatched down here at 1 gigahertz. You go up, you go around 2.8 gigahertz. The reflection coefficient goes down to like 0.18 maybe. And then it starts going up again and it becomes mismatched. So it's never really perfectly matched in this case when you have 50 ohm. You always get some reflected power back. But of course, if it's 0.18, then the power is 0.18 squared. So not a huge number that comes back. If I now change the reference here from 50 ohm to 74 ohms, then we can see that we actually get it to be perfectly matched. So now we have 74 ohms. The reflection coefficient here at resonance frequency becomes 0. This is in linear scale. This is in dB scale. So here you really go down to 0 in these cases, which is of course good, but then you need the 74 ohms transmission line, which maybe you don't have. And again, then that reflection coefficient squared is reflected power. So that means at 2.8 gigahertz here, you have no reflected power. But of course, if you have a communication system, you don't only have 2.8 gigahertz. Maybe you go from 2.5 to 3. And if you go up to 2.5, the lower edge here, yeah, you will have 0.5 reflection coefficient, which means that 25% of the power is reflected back. 75% of the power is accepted. Not so good. Sometimes this is, again, as I mentioned, plotted in dB, so then 20 times the 10 logarithm of the reflection coefficient. Standing wave ratio is sometimes used in these cases. And now we, of course, have to ask then, what is the bandwidth of the antenna? So now we look at matching bandwidth. And that means that you have to say which kind of reflection coefficient do you actually accept. So we said before, I mean, you would like the antenna to be perfectly matched, and that can only be basically at one frequency. It can be at a discrete set of frequencies next to each other, but it cannot be at an interval. It's physically impossible unless you have active matching and circuits and so on. But with the passive circuits, it cannot be done. So that means that you have to say, what do I accept? And then you say, over what bandwidth do you actually have this matching? So let's take one example here. Let's assume that you say that you allow 0.3 of the reflection coefficient. Or you can say, I allow maybe minus 10 dB or standing wave ratio 2. You can say different numbers. If we take the 0.3, then we can see that's here. And that means that I can now take the number here where I have the cut of this one, I have the cut of this. So that means that I will have an interval where my reflection coefficient is below 0.3. That defines the bandwidth of your antenna. If you now have said matching is 0.3. If I instead said minus 10 dB, of course I have to plot it in dB scale. I do the same thing down here. And then I can see I have one line there and I have one line there. And you again have a lower frequency and you have a higher frequency where this is matched. And it's approximately the same as minus 0.3, because minus 10 dB is approximately 0.3. And then you can say, okay, what is the center frequency? And in most cases here, you define the center frequency. It's just the average between those two frequencies. So it is the frequency in the middle here. It doesn't mean that it's resonant at that frequency. It's in the middle of the frequency band. And when you have done that, you can define your fractional bandwidth. And for antennas, you always talk about fractional bandwidth. You hardly ever would talk about absolute bandwidth. If you think a communication system, there you say, I have 20 megahertz of bandwidth. I have 50 megahertz of bandwidth. That's an absolute bandwidth. In antennas, you normalize it. So you talk about the fractional bandwidth as a number, like 0.2, 0.3, alternatively 20% or 30%. So in this case here, we can look at the bandwidth, and if you calculate it here, it will be 15% in this case, which means that you will take this upper frequency divided by the lower frequency, and then, or upper frequency minus the lower frequency divided by the center frequency. So that is your fractional bandwidth of antenna. And the reason why you do it with fractional bandwidth is that the antenna itself is in some ways related to only its own wavelengths. So half wavelengths dipole has the same frequency at 1 gigahertz or same bandwidth at 1 gigahertz and 2 gigahertz when you use the fractional bandwidth. But the absolute bandwidth will depend on what frequency you are looking at it. So percentage is typically what you use for antennas when it comes to this bandwidth. You can, of course, if you go out and buy an antenna, it says this one works from 5 gigahertz to 8 gigahertz. It has a center frequency between them. So then you say which is the operational bandwidth that you can have there. So a reason why these got quite similar in this case is that if you take the 20 logarithm of 0.3, it's 10.5, which is basically minus 10. So these are very, very similar in numbers. So now if you have then bandwidth, you maybe would like to relate it also to something that doesn't have to do really with the matching, and that's sometimes done with a Q factor for these antennas. In most cases, bandwidth is limited by, or matching is the limiting factor for small antennas. And the matching bandwidth is then defined as this interval where your reflection coefficient is below some number here. And typically, half power, now it was 1/3, which is the same as standing wave ratio 2. And you can do reflection coefficient 0.32 in this case, which is very close to minus 10 dB. So you can see these numbers are very similar all of them. And if we look now at this antenna, I can compute the fractional bandwidth here. So upper frequency below divided by lower frequency and center frequency. And if I have some antenna that comes here, radiation resistance, I have the reactance here, I have resonance frequency at 0.37. Then I can say now, if I'm taking half power bandwidth here, which is reflection coefficient 1 over square root of 2, because that means that half the power is reflected, I will get 5% bandwidth. If I take 1 over 3 instead, I get 2%. So the fractional bandwidth, as you have, depends on the threshold that you have for your matching in some ways. And by using Q factor, you can avoid that. So by defining the Q factor instead, you can get a quantity that has to do with these electric energies and magnetic energies. So it's something to do with the physics around your antenna. And for antennas there, which are single resonance, which typically is the way, behavior we have here, there we have that the fractional bandwidth is 2 over Q and then the reflection coefficient. So if you put in a specific reflection coefficient here, you get the fractional bandwidth out. And if we will look at this antenna, this one you could compute it has a Q of 43. And that means you get the previous result here just by plugging in what these values are of your reflection coefficient. So half power bandwidth or 1 over 3. So that is what the Q factor is for this. And the Q factor is of course related to these stored energies. So in a capacitor, you would have stored energy, which is the capacitance voltage squared over 4, stored magnetic energy, the inductance current squared over 4. And then you can just add those up in your Q factor, you divide by the dissipated power, you get a Q out. And a high Q means it's narrowband. So this is Q30, this is Q6. And this is the generic plot of a single resonance. So it can always be written as this factor of a Q as long as it's a single resonance. The last slide before we break today is what happens now with the width of it. Because I said in the beginning that the dipole resonance doesn't really change if you change the width of the dipole. It's approximate, because here we can see an example. So this is again a dipole. And now you have a width here of 0.01, 0.02 in green, 0.04 in red. And the imaginary part here, the reactance, these curves, the radiation resistance you can see here. So you can see that, yes, I was not telling you the absolute truth because the resonance frequency is changing. Okay, good. How much did it change? Almost nothing. So you can see it's still below 0.5, half a wavelength, and it's still around 0.47. Very, very small change of this. The radiation resistance, you can see it's actually changing. So the resistance for this 0.4 is higher than 0.2, which is higher than 0.1. And you can see that the slope of these curves are changing. But the value of the resonance doesn't change. So now let's look at the matching. So now if I plot the reflection coefficient here, and I do that again as the width, you can see again the bottom part is slightly shifted, but almost nothing. But the width here of the red one is wider. So if I would like to determine the reflection coefficient at 0.3, I have to go from there to there. So that is for the red curve. If I do it for the blue one, you can see it's only from there to there. So my bandwidth is higher for the wider dipole. And this is something that sometimes it's said with these antennas, is that fat is good. And that is in the meaning that wider antennas typically have a larger bandwidth. And what can be shown in these cases is actually that the bandwidth, which was inversely proportional to the Q factor, is related to something which is called the polarizability of this antenna. And the polarizability goes back to almost my first picture of the dipole, when you can see plus charge, minus charge. You want to separate the plus and minus charge as much as possible. And if you have a wide antenna, you can actually separate plus and minus more. And that actually gives you the bandwidth in these cases. So that is something that we can see that we get that. And with that, time is out. And we're also out of this lecture. So I should first tell you that the first quiz is closing very soon. I can see that some of you, a third approximately, have done all the quizzes. So if you have not done the quiz, do it now. Don't wait until the last day. The quiz will close on Thursday. I will not open the quiz if you have not finished it before Thursday. So start doing the quiz. On lecture 4, then we start looking at ground planes, image currents, and then we will come into more antennas. Because if you think so far, okay, we've done 3 lectures, we basically talked about dipoles antennas. Now we will generalize this slightly. We will go to what's called a folded dipole, and we will go to monopole. These are the simplest versions of dipole type antennas, which are not this simple dipole as I have here. After that, we will introduce many antennas basically per lecture. We will start looking at many different types of antennas. First version of the lecture notes are up on Canvas. So yeah, take a look at the lecture notes. And then for the exercise, probably the name is slightly different. The PDF file for the computer exercise is also up on Canvas. So that is the computer exercise that we plan to run on Wednesday, that will be done on FECO. So in similar way as we did the previous exercise, but we will be more people to help you. And the idea is really that you should start running this in FECO. You should see the impedance of your antennas, the radiation patterns, which is precisely what you need when you're going to design your own patch antenna starting next week, because then you will start designing a patch antenna. And next Monday, I will have a lecture about patch antennas. So that is what you will do in the lab. Okay, so with that, we will actually